This is lesson 4 for Unit 5, and with this lesson we finally get to see how you can perfectly find areas under curves. No messing around anymore with silly little ribbons that aren't going to do it perfectly. We're going to get it exactly right, and we're going to use something called the fundamental theorem of calculus. Now, you've probably heard me say that calculus is kind of like a race car, and if that was true and limits were the engine, then the fundamental theorem would be the transmission. It's the thing that kind of links going forward and going backwards in calculus. We're going to need to go backwards a little bit in order to get these perfect areas figured out. And speaking of going backwards, right away, I want to just kind of go over the notation that we have in calculus to talk about whether we're doing a derivative or the reverse of that, called an antiderivative. So we've already seen how it works to do differentiation. Okay, that's what I'm going to call driving forwards in my car. So starting with f of x, I can get to the first derivative, right? That would be, just 6x. And I can go even to the second derivative, that would just be 6, right? Going in that direction, that's called differentiation. No problem. I've got this little notation there. I can put some apostrophes on there to talk about how many times I've gone and done a derivative. Well, in order to get these perfect areas figured out, we're going to have to do the reverse of that, and we're going to call it anti-differentiation. And we're going to need a notation. Now, the actual answer is not too hard to do, trying to work backwards on this. Think about what could I put here and take a derivative of and get 3x squared? Well, that would actually just be x cubed. But what's interesting is it could actually have a constant added on there, right? It could be like x cubed plus 11 or x cubed minus 3. So we usually just say x cubed, and then we'd go plus c, just to tell people, hey, there could be any arbitrary constant there. Now, the notation for that, I get the fact that we can do apostrophes to go forwards, but how do we tell people we've gone backwards by one derivative? And the answer is this. If we've got a little f of x there, most people just go capital F of x. Now, obviously, you can only capitalize the letter once, but the good news is you generally only have to go one step backwards when you do this anti-differentiation. So, yeah, we can just go to a capital letter. That'll be fine. Now, to get to the point where we can see this fundamental theorem of calculus, I want to introduce the idea of what we call the accumulator function. This is really nothing more than, if you want to come up with a kind of simpler name, the area so far function. How much area have you gathered up underneath your function as you go for a walk? So imagine I've got some nice graph here of f of x, right? That's what this blue curve is. Just f of x, no big deal. Got my x-axis going along here. Yeah, things are great. Got my y-axis there. And I'm going for this nice walk, watching the function kind of go up and down and up and down. Things are good. But what if, while I was going for a walk, what if ever since the beginning, maybe ever since x equals 0, what if I've been just making a little note of how much area we've actually gathered up so far? Like maybe by the time you get to here, you would have gathered up a whole bunch of area in here, right? So that would depend on how far you walk. So maybe I should say, yeah, it's like a function of x. If I only walk 2 steps, and if I stopped here, I gather a little bit of area. But if I walk more, well, I'm going to gather more area. So it's definitely a thing that will possibly grow, right, as time goes by and as I continue to walk down the road. And what I really want to kind of look at is what happens when I'm at that portion of my walk where for maybe 1 minute or maybe for 1 second, what about like right in here, where from there to there, I gather up a little bit more area. Just a little bit more area gets accumulated and added to my big pot of area that I've been gathering, called this area so far. Well, I'm not going to gather up a lot of area because the function is so small there. And in the world of calculus, we could talk about that little incremental bit of area that you've added on. We could call that a dA, a small little chunk of area that's going to get added to the story. And it gets added in the story when you continue to walk down the road by a little bit more. And we're going to call that little tiny width of a walk that you're doing, we're going to call it dx. So x is keeping track of where you're at, right? That could be some nice big number saying, oh yeah, I'm currently here. But dx is going to be the extra little bit of x that you add when you go for one more step in your walk. And what I notice is that in this story, this area that gets added on, this red area, won't be very big because the function's so small. So I'm just going to leave a little note of that. The area accumulates slowly here. For that one little step to the side, I don't pick up a lot more area into my area so far. And that's in contrast to here. Here, when I go for just the same amount of steps sideways, I'm still going to do just a little additional walk, just a little dx right to the side. I'm going to end up gathering a whole bunch more dA because the graph of f of x is so tall there. So that's worth noting, right? In that spot there, area actually accumulates quickly here. Okay, well, these little ribbons of extra area that I've drawn in red that get added on, they are just little rectangles. You can actually figure out how big they are just by multiplying their height by their width. So this dA here, it would just be the current value of f of x at that spot. Actually, let me do that in red because we're adding a little bit on. I'll keep the colors consistent. So that would be the f of x at that moment multiplied by dx. And right now, at this spot, right here, this is pretty tiny. I mean, the graph's just not very tall there. But later on, when we do the same calculation, when we say, oh, look, we're adding on a little red ribbon here, it's going to be f of x tall and d of x, dx wide. When you do it there, at this point, the f of x is really big, so that dA will actually be quite large. Now, dA or dx, those are what we call differentials, small little changes. And you can move them around, kind of like grade 9 fractions. And you could actually say this. You could say, well, dA dx would equal f of x. Now remember, what I'm suggesting to you is that on this first part of the graph that we're focusing on, you know, like right here, that right now this is pretty small. Right? I mean, just look at the value for f of x there. It's pretty tiny. And over here, same thing. I could say, oh, dA dx. Just moving the differentials around. Yeah, that's equal to f of x. But look how tall this graph is here. Right up here, this graph is enormously tall. F of x is way up there. So here the f of x is really big. But now that I've moved those differentials around, what I can see is it kind of tells a story, right? dA dx is a rate and says, hey, here's how fast the area is growing. The accumulated area is growing. Turns out it's just equal to the function. When the function is tall, then the rate at which area gets gathered up is really big. And if the function's tiny, the rate at which we gather new area is actually really, really small. So it's totally fair to say that, oh yeah, the f of x, the height of the function, is the derivative of a of x. In other words, let me say that another way. F of x, the height of that function, it predicts how aggressively, how quickly we're going to be gathering up area. During times of the day when the f of x is very low, we gather up area slowly. And during times of the day when the function is very big, we gather up area very quickly. So yeah, f of x, its current value at any moment at any x is the rate at which a is changing. It's the derivative of it. Well, that's all very nice, but I want the a. I'm trying to do this whole definite integration thing and find out perfect areas under a curve. So I just reverse it. If f is the derivative of a, well, let's say that backwards. A is the antiderivative of f of x. With one minor problem. Just like we saw at the top of the page, when you go to do an antiderivative, there's this arbitrary constant in there, this plus c, right? I don't know how much that number could be. Any number in there would still be an antiderivative. So when we play this game, when we do this antiderivative of f to try to figure out how much area we've got, we might be off by a constant. So I'm just going to leave a little note in here. It just says, 2 within some sort of plus or minus c, some sort of constant. Okay, some arbitrary constant. Now I'm going to show you in a second that that's not really going to bother us very much. Not on this day. Maybe for some other stuff in calculus, but not for this issue. And we're going to see that right here on this next page. So what is with this plus or minus c? Got myself a nice little parabola here. 3x squared plus 2x plus 5. Got it all graphed for you there. Very nice, right? Cool. I like it. And I'm going to try to find how much area there is under the graph from 1 to 3. You can see in the notes there, that's kind of the big request is, could you find out the perfect answer for how much area there is? Geez, the font on this axis is pretty small. Starting here at 1 and finishing all the way out here at 3. That's my goal. Try to figure out how much area there is there. And this is how this game works with this fundamental theorem of calculus. The first thing you have to do is come up with an antiderivative of your function, right? So I've got my f of x, that's great. Now I need an antiderivative. Here's one possibility. It might be x cubed plus x squared plus 5x. That's an antiderivative of 3x squared plus 2x plus 5, because if I took a derivative, I would then get this. That's my goal. Just come up with something that you can take a derivative of and get that. But here's another antiderivative. What about x cubed plus x squared plus 5x? I don't know. What about plus 14? You could take a derivative of that, and you'd also get 3x squared plus 2x plus 5. Now remember, my goal on this page is to show you that it's not really a big deal. We don't really care. We can do this with either one of those antiderivatives. My plan, if I want to try to find the perfect area under the graph from 1 to 3, which is what this symbolism is right here, right? This means do it perfectly, get it exactly right. We'll do this Riemann sum taken to the limit, doing this definite integration. What I'm going to do is say, look, I know you only want to go from 1 to 3. And yeah, it's possible that somebody has been accumulating area for quite some time, maybe ever since 0. They might be like, oh yeah, I've been watching how much area there is. And I'm like, oh geez, I wish you hadn't started there. I wanted to start right here at 1. And then they keep on going. They keep on going. They keep on going. And then you're like, hey, would you mind stopping? But if they do that, they've actually accumulated too much area, because they might have started at 0. But that's okay. I could just ask them, well, how much area had you accumulated by the time you got to 1? So my general plan is just going to be this. I'm just going to say to them, would you mind telling me the area so far to x equals 3? And then I'm going to subtract from that the area so far to x equals 1. That should subtract that off. So my plan is to use that, like capital F, and you're like, well, which one? It doesn't even really matter. I could use any one of them and then do a nice little subtraction, right? Ultimately, I want to do capital F at 3 minus capital F at 1. That should tell me how much area there is. Now, depending on which one of those functions I use, I get a couple of different answers. If I use the first one here, x cubed, well, it looks like I'm going to get a couple different answers, but then in the end they're the same. But with this capital F1, x cubed plus x squared plus 5x, if I use that one and just substitute in 3 and then substitute in 1, the numbers that I get are 51 and 7. and I get an answer for the area of that part that I want of 44. If I try it with the other function, if I try it with that f2, the one that has the 14 added on the end, well, then I end up with slightly different numbers at the beginning. I would actually end up with a 65, something that's 14 bigger, minus, well, a 21, something that's 14 bigger. And then in the end, I still end up with 44, right? So everybody's happy here. We're going to get the right answer no matter what. So nobody cares which of those two capital F's you use. It turns out they both work, right? They both work beautifully. The only difference is where they start. That one that doesn't have the 14 added on, it actually started accumulating area at 0. So it's actually the picture in yellow. That F2, the one with the 14 added on, I added 14 deliberately because it actually is a machine that starts accumulating area at -2. So it's basically doing this. And I know this might look a little complicated at the beginning, but my point is it doesn't have to be, right? So here's -2, and that second antiderivative with the 14 actually was finding the area like this. And it said, okay, that area is 21, and if you keep on going all the way to here, then we can get 65. So either way I subtract, I'm going to end up with 44. So it's arbitrary based on where this thing starts, and nobody cares. So here's the fundamental theorem. It's a whole bunch of good news. It says we get to find perfect definite integrals. So we'll throw this in the box here. This is the fundamental theorem of calculus. Now this is actually part 2 of it. We'll see part 1 next day. I know it's a bit backwards, right? Doing part 2 first, then part 1. But this is the part that's the most important to us right now. So we're going to begin with this. And it says if f is continuous, so it has to be a nice connected function on some closed interval, and if capital F is any, can't go wrong. Like just find any antiderivative if you're trying to find the perfect area under the curve, right, which is what this says, it's like, oh, would you mind finding the perfect area under the curve using an infinite number of ribbons? Well, actually, I do mind. I don't want to sit there and add up an infinite number of ribbons. It takes too long. So I could just do this instead. I could take my antiderivative at B and subtract off my antiderivative figured out at A. I just need to come up with an antiderivative, put those two values in. Now there's kind of a shortcut way of writing that. A lot of people like to write it like this. They'll take their antiderivative, they'll put it inside a little square box like this. That's okay, I found it. And then they put their evaluation places here. There's the beginning, there's the end. And this means to go and do final minus initial, do f of b, and then subtract f of a. And that's just a short compressed way of writing this story here, f of b minus f of a. So it's supposed to be super easy. Let's give it a try, just on the next page, and you can see how nice it is to find these perfect areas under a curve. So it says find the following definite integrals, just using this theorem. This is what it looks like to actually do it. It's actually often very, very fast. I don't have to go and ask my calculator to do ribbons. I just come up with an antiderivative of that function that's there. So this one is f of x, looks continuous to me. I'm going to come up with a capital F, an antiderivative. Here's one. How about x cubed minus, this would have to be 5 halves x squared, right? It would be an x squared and then the 2 comes down. So yeah, that'll work. And then maybe plus an x. So it takes a little while to think about how to drive this car backwards, but once you get the hang of it, you'll be pretty quick. And then we're going to evaluate that at these two spots. We're going to do final minus initial. So I put the 4 in first. I'm going to go 4 cubed minus 5 over 2 times 4 squared plus 4. Get that final evaluation done. and then subtract off the initial evaluation. Final answer for that ends up being 28.5. Perfectly found the area under the curve. I can even do it with radicals, with roots. It's not a big deal. I might just want to rework their question. Right, I might want to say, okay, we're integrating, finding the area under the curve from 0 to 1 for x to the 4/3 dx, right? That's a cube root, and then to the 4th power. And the deal is always the same. They give you that little f, and then you have to go backwards to find the antiderivative, right? So sure, this is the little f. Now we've got to do an antiderivative. Personally, I do it like this. I always try to get the exponent right first. So I would sit there and go, okay, instead of 1 down, I have to go 1 up. That would be 7/3. Now, if I took a derivative, this 7/3 is going to come and crash the party. I need a little bodyguard here to take care of the party crashers. So when that 7/3 arrives, I don't want to see them. So I'm going to put a little protective 3/7 out front. That way, when the 7/3 comes down, it'll just vaporize. It's gone. Okay, evaluation box, 0, 1. Put the final number in first, so I'm going to put the 1 in first. You end up with 3/7, and then you subtract off putting in the initial number, the 0. Okay, the perfect area is 3/7. Now this one here, there really isn't a nice product rule for these things. So my advice would be simplify. Whenever you can, you want to simplify. So I'm going to rewrite their question. This is actually 16 x squared multiply and double plus an 8x plus a 1 dx. Okay, antiderivative. Again, I just write down the exponent first. I'm going to have to go up by 1. And then I think of a little bodyguard. I'm going to have like a 1/3 bodyguard. And the 16 just hangs around. So this will be 16/3. And if you find that troubling, just imagine taking a derivative. Just try it. Like picture doing a derivative in your head, and you'll see that you'll end up with 16x squared. This next one, it's going to have to be something x squared. Oh, that'll have to be a 4 in order to create the 8. And this one's got to be an x. I'm just doing the game of derivatives backwards. Okay. You put the 2 in, you put the 1 in, and you subtract. When you put the 2 in, you end up with, I think, 182/3. When you put the 1 in, you end up with 31/3. Okay, you subtract, and you get 151/3. This one here, integrating sine. Okay, be careful. You have to think, what could you take a derivative of and get to sine? So I'm going to do my antiderivative. The 2 is going to hang around, so I'm just going to draw that in here. I know that sine and cosine generally flip-flop back and forth. I might start by just writing down a cosine and then just kind of stare at it and ask myself, if I took a derivative, would I end up with the sine? And the answer is no. If I took a derivative of this, I'd have minus sine. So, okay, no big deal. Put a little negative out front. Now we're fine. And now we'll evaluate this from 0 to pi over 3. So we would be going -2 cosine of pi over 3. Get that done. And then subtract -2 cosine of 0. I think the answer ends up actually being a 1 on that one. Okay, the next one. These next two, they come kind of as a pair. I've got an integral of 1 over x dx. This one is different. It's all out on its own. It behaves a little bit differently. You can't think of this as being a power rule. If you try, if you're like, oh, okay, I can do that. You know, this is just x to the -1 dx. If you try thinking of that as a power, you end up kind of getting into a little bit of a log jam. Instead, you have to look at it and go, oh, I know that one. I know this thing that I can take a derivative of and end up with 1 over x. It ends up being ln x. So we're going to take ln x and then evaluate it at 2 and 5. With the final one, subtract the first one. Now I'm going to leave that there just for a minute. We're going to change it slightly, but I'm going to leave that there for a minute and then look at this next one. Okay, so we're finding the area under the curve, 5 over x, from -2 to -1. And at first, I'm thinking, okay, well, the 1 over x part's going to turn into a ln, and the 5's going to hang around, because constants just hang around. And sure, we'll go and evaluate. But I can't go and put negatives into this ln. And then I remember back a couple of chapters, we were talking about how if you take a derivative of ln x, you get 1 over x. But if you take a derivative of ln of -x, you also get 1 over x. And so we're always going to look at this and say, hey, this is a perfectly fair question. You couldn't graph that and find the area underneath it. But we run into troubles if we try to drop in the -1 and the -2 into this story. So whenever we're integrating 1 over x, we're always going to put absolute value bars on the x. They have to go there just for safety reasons. And then in this first story, okay, this one would just be the ln of 5 minus the ln of 2. Do absolute value of 5 and 2, nothing happens. This one would be 5 ln of, I do the last one, it would be a 1 after the absolute values take care of that negative sign, minus 5 ln of 2. So we're going to remember, we're going to agree that if you ever have to do an integral of 1 over x, we're going to write down, oh yeah, it's just ln x, but we're going to put on absolute value bars like that. Okay, always have to go on there. All right, next page. The next page is really just for fun. We're going to kind of look at some physics stuff and then look at what could go wrong with non-continuous functions. But first of all, some physics stuff. The only reason for example 2 is just so that you can see how the world of physics kind of blends in with this world of calculus. So I'm actually trying to integrate some forces here. And when I do that, I'm going to end up calculating energies, right? But these are definitely, just looking at them, that's a spring force. So this is not something that you need to know for calculus, but I just want to show you how wonderfully well this calculus world works. And this is gravity force. Well, this gravity force question, I'm just going to rewrite. I'm going to say, wait a minute, that's the same thing as integrating from A to B. I'm going to write that as a power. There's this G, M, M, and then it's r to the -2 dr. Okay, well, if I do an antiderivative for kx using x's, I'm going to end up with something that feels like x squared. And the k will hang around, but I'm also going to pick up a little 1/2 bodyguard. And I'll have to go and evaluate that at these two spots. The final value b, and then minus the initial evaluation at a. And really all we've got here is energy. That's the equation for spring energy, right, in the world of physics. Well, when I do this antiderivative, right, the g and the m, those are constants, they hang around. When I do the antiderivative of r to the -2, I'm going to end up with r to the -1. I have to go up by 1, and then I need to put a little negative sign bodyguard in there. So this is just for the physicists so they can look at this and go, oh, okay. And you end up with negative g m m all over r, which was one of our stories from Physics 12, right? Where you're like, oh yeah, when you're doing gravity energy calculations, you actually have to use that energy equation twice, right? The only way you could get correct answers in physics was to use that equation twice and subtract. And it's really just an antiderivative that you're doing. Next story, this one's kind of neat. We're going to see if we can find the area that's shaded up above that curve e to the -x squared. And at first glance, I'm thinking, okay, well, that shouldn't be too bad. You know, if we can just find the area under this curve, maybe we'll ask the calculus to do that from 0 out to 1.5. Then we can take that answer and subtract it away from just this whole rectangle here. You know, the big rectangle is not too hard to figure out. In fact, let's do that right now. That's going to be 1 tall by 1.5 wide. Okay, the units, the area there are just 1.5 square units. Okay, so if I want to find the area kind of shaded in dark, I'm going to find the area shaded in green by me using some calculus, and then I can subtract. But here's the problem. I've picked this one deliberately, because if you sit here and say, okay, we just have to go and work with this, e to the negative x squared dx, and try to do an antiderivative of that. It's kind of weird. For calculus, no matter what the function is, you can actually take a derivative, but you can't always find an antiderivative. And it turns out this function does not have an antiderivative that you can find algebraically. So there just is no antiderivative out there. Doesn't exist. But the question is still a fair question. How much green area is there? So what you have to do is ask your calculator. Okay, there's no other way around it. You just say, hey, calculator, I'm over my head. And this happens to us in the world of math and science a lot, where you just have to say, yeah, it can't be done. Not by algebra. So I'll have to grab my calculator and say, hey, help me out. So maybe I might go and graph this. I might say, okay, let's put a y equals in. I'm going to put in e to the negative x squared. And I'll graph that. You know, zoom 4 is probably fine for now. Okay, there's the graph. And I want to know how much area is there from 0 out to 1.5. Maybe I'll zoom in a little bit, make it a little easier for you to see. So I can't do this algebraically, but I could ask my calculator to do it numerically. Say, hey, can you do a number 7 here from 0 to 1.5? And then on my calculator it says, well, I can do that. Use the little Riemann rectangle thing, and I got 0.8562-ish. So if you really want to know how much area there is up here, that area, well, we'll subtract. We'll go big pink rectangle, 1.5 minus this 0.8562. Ends up being around 0.6438. But there's no way that I could do that one algebraically. I just wanted to show you that sometimes that's what happens. We end up with these stories that you can't solve algebraically, and you have to trust your calculator. Here's another thing that can go wrong. They're called improper integrals. And you'll study these in university, but they're not part of our course. They're not part of Calc AP. So we just need to look at these for our version of Calc AP and say, no, these should not be questions that we do. And these would be stories where your function that you're trying to find the area underneath is not continuous. There's something going wrong during the time you're trying to do this integration. So this first one, it says, hey, would you mind finding the area underneath that from 0 out to 2? Well, this graph gets infinitely tall. And the area just leaks way out the top when you first start this thing. And then you go all the way to 2. And actually, when you study these indefinite integrals, you'll see that this one is infinite. There's an infinite amount of area there. You'll never be able to paint it. And so we just need to know, like, well, you wouldn't want to do that one because when you start at 0, the graph is not continuous at 0. It has this big kind of gap in it there, this asymptote there. This next one also has an asymptote there, but what's interesting about this one is if somebody says, hey, can you go from 0 to 2, and you try to find the area under this one, even though it goes up to forever, it's really thin, and it has an answer. It's actually 2 root 2. So these things, my point here is they can be confusing, and we're just going to not do them. We're going to walk away from them. This next one, that particular function actually has a hole in the graph right there. There's a little gap in it. And if somebody says, hey, you wouldn't mind integrating, would you, from 1 to 3, starting here and finishing here, we're not going to do that because all of a sudden there's this little gap in there and it's not clear how that's going to pan out. Now, in university, when you go to work on this, you might find that, oh, okay, well, yeah, you can get it to work and the answer is 4, but we're not going to do it. We just need to know that these are not for us. We can also have improper integrals if you integrate out to infinity. So this story, 1 over x squared, that didn't work very well in the first picture, actually works okay if you start at 1 and then integrate to forever, even though you're going to like forever. And the answer for that, turns out it's just 1. So, it's confusing, right? So basically the plan is this. Let's agree we are not going to do those. Not in our course. Okay, I just wanted to show you they're kind of unpredictable and we're just going to say, yep, they're simply not for us. Okay, well, the next 2 pages, we're just going to have a little bit of fun looking at a little story about a chipmunk just to try to get comfortable with how this whole idea of integration is actually working. So I've got this little graph here, and this graph up above, the little f of x, is the speed, the rate at which this little chipmunk here can gather up nuts for the winter. So the upper graph, little f of x, this is the chipmunk's nut gathering rate. And it's going to predict how fast, down below, for capital F of x, this chipmunk can actually go and accumulate some nuts. Store of nuts for the winter. So the units for this lower graph are going to be in nuts. But the units for the upper graph, this is the rate at which we're gathering nuts. So this could be like nuts per day. And it looks like on the first day we're gathering up 3 nuts per day. Okay, so you're going to put 3 nuts into the bag. On the second day, we're gathering in 2 nuts per day. And then 1 nut per day. Right, and then the nut gathering rate goes way, way, way up. And if you just go and count those little nuts, then you can actually see what the values are for the graph down below. So down below, after the first day, we've gathered up 3 nuts. Then our nut gathering rate up above drops down to 2, so we're only going to gather 2 more, so we'll get 5. Then our nut gathering rate goes really low, just down to 1, so we're at 6. And then still 1, so 7 nuts in the bag. Then our nut gathering rate goes up to 2, so we're at 9. And then we gather 3 nuts, 12. I'm just kind of eyeballing the graph up above to see how many nuts I'm going to gather each day. Then I gather 4, so 16. And I gather 8. Whoa, big growth in the amount of nuts in the bag of nuts. And then another 8, 32. And then still a good day, 4 more nuts, 36. So this accumulator is actually keeping track of the total amount of area underneath this graph. It's just the nuts so far, right? So I'm going to put a little blocker in here. If you've only done 1 day, you've got 3 nuts. If you do a couple of days, now you got 5, right? Do another day, now you got 6. Do another day, now you got 7. That's all we're doing. We're just saying, yep, we're gathering up area underneath that nut gathering rate graph. So you can actually look at this graph and say, yeah, it's controlling how quickly the nuts are growing in that accumulator. So I'm going to put a couple of notes in here. This rate, f of x, controls how fast capital F of x grows. So you could say that f of x, little f of x, is actually equal to the derivative of the accumulator. Right? It's predicting how quickly it's going to grow. And if we look, this little f of x is small here. So we're going to see small growth rates down below. But little f of x is really big here. And sure enough, when we go and look at the graph down below, we actually see that effect showing up. So right at the time when the nut gathering rate is low, what we can see is that our bag of nuts is actually growing slowly here, right? So capital F of x, our accumulator, increases slowly here. But here, capital F of x increases very fast here. Simply because that upper graph is so tall. So, a thought about what's happening here. It looks like capital F of x is the accumulator of little f of x. And we find those values by doing an antiderivative. All right, one more page of looking at our little chipmunk here. Riemann sums. Back a day when we were looking at ribbons, we said, oh, you could add up a whole bunch of ribbons. That's all Riemann sums are about. Okay, just when you see that idea of Riemann sums, we're just adding up some ribbons. And as I look at this addition to try to figure out what's going on here, this is figuring out the height of each ribbon. And this story here is the width of each ribbon. If you take that as a limit where you do an infinite number of ribbons, then you can get to the right side of the page. Okay, then you can say, hey, this will be a perfect calculation over here. But in order to go from the left-hand side of the page with Riemann ribbons over to the right-hand side where it's perfect, you would have to do a limit. You would have to actually take the number of little Riemann ribbons and take it to infinity. Make each one infinitely thin. Then you get perfection. So the left side, maybe not so perfect, right? This is just an approximation over here. But you can make the approximation perfect if you do a limit to an infinite number of ribbons. Now, a couple little thoughts, and the chipmunk's going to help us out with these last little thoughts here about how the numbers are going to work out with plus and minus signs. The first story here is about a chipmunk who for 4 days actually gathers up, well, negative nuts. So these are like spoiled nuts that are going to ruin the other nuts that are in the bag. So this would be like bad nuts. And if you ever find yourself integrating a function, okay, I know it's a cute little picture of the chipmunk doing his accumulation, right? That's great. But if you find yourself doing a story like this, where we're accumulating from 0 to 4, so we're walking to the right, right? We're doing a right walk. That's why my little green arrow's there on my chipmunk. He's walking to the right. And if you find the integral with a function that's in the negatives, like this one is, if you know this function the whole time is negative, then you're gathering up bad nuts. And in this case, the answer would be negative 16, because you've been putting bad nuts into the bag. Sometimes you end up with a function that kind of swizzles around and spends some time up above and sometimes down below. So I'm just going to call this like canceling areas. Now, if you were actually looking at area, like, oh, gee, I need to go and paint this. I have to go to the hardware store. I'm going to go and grab some paint because I want to paint this graph and paint that graph. Well, you'd need positive paint. I mean, if there's area there and you have to paint it, then you need paint to do it. So it's kind of a weird issue with just the names of things, right? So the area here would be 6 plus 6, and it's like 12, yeah, if you have to paint it. But if you ask calculus, hey, calculus, what do you think if we were to go and do this definite integral from 0 to 4 of f of x dx? then the calculus is actually going to say, well, those first nuts are great, but then the next nuts are negative, and the calculus is going to give you a 0 answer. So we have to be ready for that, right? If people ask you, well, no, we're going to have to paint it, be careful. You wouldn't want the answer to come out to be 0 and say, oh yeah, we don't need to buy any paint. It's already done, right? If you have to paint it, the paintable area is 12. But if you do the integral, we're going to say, and we want it to say this, we're going to say that the integral is 0. So be careful about that issue. It's something we're going to be looking at a lot over the next little while. Next issue, what if you integrate backwards? So these are perfectly good nuts, right? These are positive nuts, right? They're up above the x-axis. Nothing wrong with these nuts. Okay, they're good nuts. But our chipmunk is walking the wrong way. So if you're ever asked to do an integral like this, an integral from 4 to 0 of f of x dx. In this case, it looks like the f of x is beautiful, right? The f of x is positive. These were good nuts. But the dx's, those are the widths of those rectangles. If that chipmunk's going to walk backwards like that, then we would say all of the dx's are negative. And so in this case, when you multiply positives by negatives, you get negative nuts as you throw them away. So this is going to be a negative 16 from the calculus. The equivalent, you know, you're throwing away good area, right? You're throwing away good nuts. All right, well, what if there are bad nuts, right? What if they're hanging down, you know, below the x-axis like this? These are negative nuts. These are bad nuts. This is a bad function. And then you find yourself integrating backwards. And this is like a squirrel looking through its bag of nuts and throwing the bad ones out, right? So they're actually going to be better off. And in this case, if you were to ask the calculus, hey, calculus, what's this integral going to look like if I integrate from, sorry, I'm going to change this around. I meant to go 4 to 0 because this chipmunk's walking backwards. From 4 to 0, so it's a backward walk, and it's a backward walk with backward nuts, with bad nuts. Then when you go and think about the little ream and ribbons here, we're actually going to have negative for our f of x, and we're going to have negative walks. And this is one case where 2 wrongs make a right. This is if you were to talk to the chipmunk, you know, and ask it, hey, what's going on? It would say, well, yeah, I'm walking backwards, so I'm throwing stuff away, but I'm throwing away bad nuts. So I'm actually ahead by the time I'm finished. And in this case, just kind of looking visually at how many nuts there are there, this would work out to be positive 16. Saying, oh, well, you walk backwards. Normally that'd be a negative. You got a bad function, an upside down function. Normally that'd be a negative, but in this case it's actually a positive. And the fundamental theorem will do that. Like it'll automatically make all of those adjustments for you, which is kind of neat. And so today we've been looking at the fundamental theorem of calculus. It's actually part 2, where you can find perfect answers by going and finding an antiderivative and then substituting in your beginning and end values, and we do our final calculation minus our initial calculation. It does a beautiful, perfect job of finding out the area under the curve. Fantastic thing to be able to do. One of the 2 main questions of calculus, that and slopes of tangent lines. Now in the next lesson we're going to look at fundamental theorem part 1. It's not used as much, and it's actually kind of really quick and easy to do, right? We'll see that in the next lesson.